I just wanted to take this opportunity to welcome you. Patrick McCafferty is actually going to introduce Jun. So I'm introducing Patrick, who's introducing Jun, who then I will reintroduce to you or something. No, just very quickly, I wanted to tell you that this event that we're having is part of a plan for us to do more things with people who, like Jun, are coming from the arena of kind of technology to the school. We have given this lunchtime series a kind of broader title called Technologies of Design, basically meaning that people who are dealing with materials, structures, building systems, we want to have more events at lunchtime that really focus on this. I was very lucky to spend a bit of time with Jun in Tokyo and have a reasonable sense of all the exciting things that he's working on. We thought that it would be a great thing for us to have him here. So I just wanted to welcome you and say that if you have any thoughts or suggestions about similar things that may be helpful to what you're doing, that would be a great thing if you can let Chantal know or let me know so that we can really begin to build up this particular set of themes. We've done something similar in the past under the rubric of a program called Now, which was basically using the kind of lunchtimes for more seminar type format. But I'm really happy that Jun is here. I'm very happy that Patrick is here to introduce Jun as well. Thank you.
So thank you all for coming to what's going to be a very fascinating talk. I'm absolutely positive and sure. It's very interesting. Actually, Jun and I realized just how small the world is. We have a mutual friend in Tokyo, actually, a good friend of mine, Mits Canada, who was my flatmate in London, so who is now teaching for us in Tokyo. So the world is like this small, so it's fantastic. Anyway, Jun Sato here is a principal engineer at Jun Sato Structural Engineers Company Limited, and he's also an associate professor at the University of Tokyo. He is trying to develop light, ductile, transparent structures as a filter for the environment through his collaborations with architects, workshops with students, and research. Such projects include Extreme Nature for the Venice Biennale in 2008, and Balloon with architect Junya Ishigami, House NA and Naoshima Pavilion with architect Sou Fujimoto, Sunny Hills, Japan with architect Kengo Kuma, and a glass structure seminar and workshop at Stanford University. I understand you're also teaching at RISD this next week. After he received his Master of Engineering degree at the University of Tokyo, Jun worked at Toshihiko Kimura's office from 1995 to 1999 and received his Doctor of Engineering degree at the University of Tokyo in 2013. He received the Japan Structural Design Award in 2009. So without further ado, I'd like to ask you to join me in welcoming Mr. Jun Sato.
Thank you so much for Mosen and everybody to invite me. I'm so happy to be here today. I'm gonna tell you some tips. Maybe it will be helpful for your projects. And I have provided the handouts, and it takes always in usual, it takes almost 3 hours to tell you everything, all of them. So, but I'll make it short. I will try to make it short this time. All right, we don't have time. Let's start. I'm now focusing to transparent structures, like transparent or translucent structures, like these mesh structures, or using translucent materials like this. And through those transparent and translucent structures, I'm feeling it can work. It also serve as environmental filters. It is coming to a very complex shape like this. And how to realize these complex shape? We could compose the design method, or like something operation of story from understanding material or to construction. We can have those complicated targets. We can have some strategy for those complicated targets. Those practices I'm trying with 3 sessions. One is dynamics operations, and 2 is geometry operations, and 3 is a workshop scale or experiments. Using these operations or manipulations, we can develop the more morphogenetic forms based on geometry or materials or dynamics, craftsmanship, and side matters. Or we can perform the spirit of engineering. This time, I will show you some projects, how these operations are composed. At first, dynamics operations. I'm researching the glass structures. So I have tried several times already the actual projects using glass structure. One is this extreme nature in Venice Biennale 2008 with the architect Junya Ishigami. His idea was building like this greenhouse, 4 greenhouses around Japan Pavilion in the park of Venice. And his idea was like this. This is the first model, or using like this transparent material. He says this is a thing. This should be thin glass, and this is the structure for plants. So, and his proposal was without using like air conditioner or something controlling humidity or like that. Without that, only covering with glass. We can make a little different climate from exterior. So a little bit different plants can be grown in this space. And this is a space for plants. So, so those bothering things, air conditioner or like that machines, or also the structure should be vanished. He requests me, and he says, of course, like this structure is possible by thick glass. To make the large box by thick glass, it is possible. But he says when the glass comes thick, it doesn't look transparent. And his request was this columns and beams should be as thin as possible. And in this model, you can see this black line. And here you can see the black line. These are columns and beams. His image was like this at first, and he asked me how we can what's the strategy to make it make this structure feasible. But. Yeah, really, it is easy to say than none. I asked him, is that your problem or my problem? And I'm saying to I sometimes say to architect or some other people, or we are the realizer of the structure. So it was so annoying, but I have practiced as many as possible, or which techniques I have. And basic idea is like this. Maybe you know the buckling, controlling the buckling phenomenon is important. You know, on the center, this is a simple or basic buckling phenomenon of the thin column. And it has like this formula here. And for buckling phenomena, boundary condition is so important. Like this hinge, and node sway, we can think this to be a basic one. And if we could make fixed and fixed and no sway, it comes 4 times more stronger than this basic one. And in the other hand, fix and hinge and sway, it comes 4 times weaker. And so the target is, of course, this one, fix and fix. But we cannot achieve the perfectly fixed one. So we should think how we can make it close to fix. And the important thing is if it is 4 times stronger, as the buckling strength is proportional to the, I mean, inverse proportional or to a square of length at here. And so if it is 4 times strong, the length can be thought, I mean, buckling length can be thought half of this length. And like that, imagining the buckling length with buckling strength with buckling length is really easy to imagine. And with Junya Ishigami, while developing ideas with him, we try brainstorming, discussion again and again for hours. Sometimes it comes 5 hours on each day. And meeting to meeting, we try to discuss as long as possible. And he doesn't say, he cannot understand dynamics. But he doesn't know. But he doesn't know this form. He doesn't know this formula. But he knows he should control the boundary condition, and he should control, or we should control the buckling length. So he asks me how to shorten the buckling length, or like the boundary condition. How about making the base plate or joint as rigid as using thick plates, or how about the expanding the bottom of the columns? I don't know how to do it, but how about expanding or like that? He proposed to me. And sometimes it is, he says, he tells me it is something strange theory of physics. But through those detailed thinking of each phenomenon, sometimes a new idea can be generated. And this time, I got an idea, got a new idea like this. Imagining the steel frame like this, with gravity, it deforms like this, and it has a bending stress like this. This is bending stress diagram. Around here, it is big, and for column, a little bending stress is generated. So my idea was reducing this deformation at the same time reducing this bending stress on the column in the column. The strategy is like this. At first, strategy is using heat cambering of steel. Or the craftsmen, steel craftsmen have really excellent techniques, like heating the steel. Or I don't know you know or not. When the steel is heated, like with burner or welded, it shrinks. So that's the character of steel. And if we could use it effectively, we can do like this. At first, without thinking, build the columns and beams straight and straight. And after that, imagine, and because the glass plates are so heavy, so imagine when the glass is loaded, it will deform like this. And for imagining this deformation, we should realize the same deformation with like these weights. And these are so heavy weights, and I could realize this deformation. And after that, the steel craftsmen will burn and camber, or make the camber with heat. And by gas burner, they're gonna heat them and shrink it like this. This guy is heating here, like dot and dot and dot. He heat, and the beam shrinks and comes up. And finally, if the beams are reformed to flat, these weights should be released. When it is released, beams comes up. But when after that, when the glass is loaded, beam comes again. They're flat. And in this process, the column is not heated, and so these columns comes straight, vertical and straight. That means the column doesn't have curvature, and so the bending moment, bending stress is not generated. This is a little complicated process, but like this, we could achieve the thin column. We could reduce the bending stress, and we could make the column thinner. And also, I have developed the optimization software for this project. It has a random located column, and I have provided the manual form of optimization software. I will show you later. And using this, I optimized the location of columns to manipulate the distribution of load. And finally, we could make the lower greenhouse. It had 2 meters high with 16 millimeters column, like this size. And for about 6 meters high, we could make it 32 millimeters, like this size of columns and beams. And finally, I think we could realize the transparent structure, and for like this, plants are located, and maybe Junya Ishigami is satisfied about this. Maybe. And for glass structure, I'm practicing another project in Netherlands. It is in the park in Vigersburg. This is also with Junya Ishigami, and like this is now under construction, and it has like this plan, and in the center there's something meeting space or some. This is for like a rest house project. And also, Junya Ishigami and Marieke Kumus in Amsterdam is collaborating. For this project, I proposed the glass wall structure like this. It is built like under construction like this, and the glass walls are located. And at first, I have provided the how to manipulate the distribution of loads. So I have proposed how the beams should be arranged. And after optimization, little transformed like this beam arrangement has been found. And also, the curved wall is so strong. From like this buckling analysis, it has found almost 4 times stronger than straight flat wall. And so finally, we could achieve like this with only glass wall structures, and it is built. It is under construction like this. Here, it is located. There's located the curved glass, and this curved glass is not transformed with heat. It is called cold bending, and it means elastically it is bended, and when fixed to the foundation, it can keep the curvature. And my research about glass structure is like this. I'm researching now, or like one of them is like this. I'm calling it stained glass structure, with like this thin frame, and the glass plates are fixed to the these frames, and work as not only the quake-proof wall, or also the vertical for the gravity. It should work. And because these thin frames are critical about the buckling phenomenon, we should control the buckling phenomenon and plastic state of material. And you know, the material have the elastic and plastic states. I mean, like plastic behavior means sometimes it is called ductile, or something ability of deform. In Japan, we have a big earthquake, so we expect the material to absorb energy by in a plastic state with plastic behavior. And finally, this structure is composed of really diverse elements, and it has diverse phenomena, like composed of multiple materials, and it has bar elements and the plate elements, and some optimized framework like this pattern can be optimized to have strong, to make it stronger. And we have here the cushioning material, or I'm proposing that to use tin kind of metal, or is useful. And the tin works as elastic material. Or it is a little complicated, but yeah, it works like that. And also the mutual buckling resistance between these frames and glass will work, and we should find like that affection. And also the plastic behavior should be should be considered with buckling behavior. If the column is thick, buckling behavior is not so critical. So we can focus to the plastic behavior. But when it comes thin like this, the both plastic and buckling interacts each other. So that is important. Like that, with like this complex structure, diverse with diverse elements, I'm thinking this structure is representing some kind other kinds of complex structures. So if we could have the strategy to how to analyze or how to realize these structures, it will be helpful for other structures. And I showed you one of the optimization software, and from here, using the optimization software, which shapes can be realized. This is the community center in Kawatana Onsen in Japan with Kengo Kuma. It has like this polyhedral form and generated by adjusting the nodes. I will show you later. It has like this shape, and the structure is like this. It has steel frames like this, and it is covered by concrete surface. For this project, I have provided like this software. It is like this. Once, just a moment. Once it is calculated, oh, this is the simple model or for the sample. Once it is calculated, it has red elements like this. This diagram is showing the blue have enough strength, and comes green, yellow, orange. It still can. It is the how to say safety ratio is reducing, and but orange is still possible. And if we have red lines, red means impossible, or it is too weak. And this software, for this software, I program like this using mouse. You can transform the shape like this, and what you have to do is find the shape without red elements. Oh, now red has vanished, and so this shape is possible to build. And around here, the blue elements are there are a lot of blue elements. So maybe this can be inflated like this, but like this, it is impossible. Of course. And so, like this, you can find manually which shape is possible and which is impossible. And using like this software, it is applicable for many other shapes. This is also the polyhedral shape, and this is made of like this mesh structure with Sou Fujimoto. And this is Freeform for House of Peace. It is called Hope. It is now under not yet started, but last year we won the competition, and it will start soon. And this one is also in the design phase. It is in Sydney. It is called Cloud Arch, like this ribbon-like tower. It will have 60 meters or 70 meters. And also with Junya Ishigami. Here's a sample for the Freeform. This is another project. This is a little secret. Don't tell to anybody. This is for Venice Biennale next year, but I don't tell the detail. All right. This software it can be like this performing like this calculation here, and you can see the red elements around here. And for this project, I have provided like this transforming program. When I pick one point, the around there will be smoothly transformed, and so you can find the freeform, which freeform is strong, and using like this, it is a little difficult. You can see. Freeform is a little difficult, but you can find. Maybe it takes time, but you can find. Oh, around here, the red has vanished, but around here, it is still red. And so, like this, you can find using like this this software. And also, I have programmed, this is not for this project, but like this can be possible. This is adding column operation. You can add the column one by one, like this, and you can find how the columns should be located. It comes blue. And like this, just a moment. Maybe this will be better. For this Cloud Arch project, I have programmed like this software. It is also, it has like this shape, and of course, it is possible to move like this and deform, transform smoothly the whole shape. And every time the red to blue is indicated, displayed like this. And I also programmed looking at the. This is a close-up around here, and you can see the sections. This is it has the rectangle section, and looks like a ribbon. And I have programmed like this. Like this. You can see the section is twisted like. When I move like this, you can see like this, and every time also the color will be is changing, and like this. And around here it is also twisted smoothly, and finally, we should find how it should be twisted, and the target will be like this image, twisted like this, twisted and waving tower. And this software is the character of my algorithm is in many cases optimization is performed against the gravity, but my algorithm is applicable to several load combinations and several load cases. At the same time, it can be considered, such as gravity, seismic load, or snow or wind is possible, and it can be combined. And yeah, so at once, after transforming the just 1 or 2 seconds, the color is displayed. But in just like that 1 or 2 seconds, many calculations are performed. Like for gravity calculation and X direction earthquake calculation is performed, and Y direction. And finally, the checking program, strength checking program for each element is performed. And finally, the colors are displayed. So many calculations are performed in just several seconds. And this software is also applicable to use by like plugins. If you're good at transforming by Rhino, or you can compose like this software. I'm not so good at using Rhino, but my staff has composed like these components. Here it has the hole shape, and when you just a moment, when you push this button, when you push this button, then automatically my software is executed, and the color is shown like indicated like this. This is almost half automatic, and maybe if you want more interactive software, this can be like real-time displaying software. It can be developed. And this shape is also adaptable for like this stacking system, like this. This software, this algorithm is like this here. When it is like this when the two volumes are stacked, the calculation has done, and here's the red lines. And if you move the one node, this volume will come like this. Oh yeah. And you can see if it is arranged like this, it is easy to build. But of course, the cantilever is so hard. You can know by this software. For like these two elements, it is easy to know without using like this structure. But it comes a little hard to know my human's brain if it comes like this. This is Sou Fujimoto's proposal of the like this curved wall or something like free-formed spaces are stacked like this. It is a little hard to know where, how we should operate these frames. When I move 1 point, it is sliding, but yeah, I'm not sure how now. But this is adaptable for like this structure, like this shape. And finally, Sou Fujimoto proposed like this building. It has 100 meters high, and like the free-formed volumes are stacked like this, and it has large porous area, space in the center of this. This is not our real project, but yeah, his idea was inside like this architecture, we can feel like under the big tree and sunlight, like that, sunlight comes in. And also the house NA with Sou Fujimoto. I have tried the optimization like this, free level floors. And the parameter of the optimization is, I showed you, is safety ratio for the stress by gravity or earthquake or like that, and it has a possibility to use like this energy absorption by seismic vibrations. This is not yet developed, but I'm trying to develop like this software. And what you have to think is how to transform the shapes to optimize the structure. There are some ideas like topological optimization or density optimization or stress-based optimization. Density optimization is stress-based optimization is easy to understand. Arrange strong elements, strong components onto stressful area. It means arrange strong, thick column to stressful area or like that. And density optimization is also easy to know. If you could find some area really stressful, you can put the dense elements. You can put many elements to have to increase the density. And there are topological optimization. I think this word is not so much exact word for in the meaning of mathematics, but it is easy to imagine. It means manipulating the stiffness or stress by transforming the shape. I showed you like this freeform or polyhedral shape, or like also controlling the floors is maybe topological optimization. And I think I don't know. There's a word genus in topology. It means the number of holes of the surface or that object. This idea is not so much related to structure. Rather, it will be related to environmental matters or something like space continuity. So it should be also manipulated at the same time with structure and environment. And from here, you could know the steel fabrication is so important. And I'm trying, I'll make it short, I'm trying like this steel meshed structure or like this steel mesh structure, or like this using thin plates. It has only 6 millimeters and without backboard of shelves. Like this structure is possible by controlling the buckling phenomenon. Like this, if the thin plates are located in a radial way, it comes so strong, and it comes 4 times stronger than parallel arrangement. And finally, I could achieve this structure by only 6 millimeters steel plates. And this is another steel structure using aluminum pipe and fabrics. It is understood as one of the tensegrity structure because the compression elements are not touching. And this is so light and soft structure. It has 26 meters long and 8 meters wide. But when 40 students come around surrounding this structure, they can lift up by their hands. And for this structure, what I have calculated is only these. I didn't use computer or software if we like this, we have the techniques to simplify the structure. I think omission is one of the technique of engineering. And finally, we can calculate with only these calculations. It is not written in English, I'm sorry, but the detail is like this. Only like this, less than 10 calculations, it can be checked whether it is possible or possible to be stable or not. And from here, the geometry operations, what I call all the geometry operations is like this. This is Sunny Hills in Aoyama in Tokyo with Kengo Kuma. I have tried the 3-dimensional or complicated Kigumi structure. Kigumi is a Japanese word. It is a traditional timber work, timber joint system. And I have developed from like that traditional system, like that really complicated shape. But I thought this is very much looks like a filter for something light, sight, or air, heat, sound, or air. Or maybe for an ecosystem or like that. So with like this meshed structure, we can control or like that environment. It is so complicated, like this. It is carved by carpenters. You can see this photo. It is carved in many different angles, but they could. But finally, they could done all of them, and it could be constructed. This system is, it looks really complicated shape, but it is understood very simple, understood as a simple system. The one component is so complicated, but the growth process is so easy, like stacking box cells. Just stacking one by one, we can make the whole shape like this. And because of the easiness of like that growth, we can make random shape. We can build up the random shapes like this, and each one should be evaluated by something parameters like safety ratio or strain energy or other elements like structural elements like environmental factors or space volume, whether it is wide or not, like this. And because the growth process is easy, the feedback is also easy. When we have the target shape, we can easily know how we should arrange these components. But sometimes this feedback is sometimes there is a system. It's not so easy to have feedback system. How to say? I heard this is called I in Spanish letter. Somebody know? All right. It is called ICube. This is with just a temporary pavilion with Nihon University students. Like this cube is jointed. Around cubes, maybe 4,000 cubes have jointed at their nose. And in this system, what is difficult is when it is connected like this, from node to node, it should have, when we think this edge as 1, this distance should be 1 or √2 or √3. We can only have 3 patterns. And so when we think about how to add one element to this structure, it is so hard. In most of the case, this distance is not those 3 patterns. So this operation is so difficult once it is imagined. But in the construction, we could feel it is not so hard to add a cube. It was like I thought it was because it has like this system. At the joint, something a little loose or something flexibility we could have around here. Here it is jointed by a like question mark joint. So it has a little flexibility, and I thought it is considered as fuzzy node. And fuzzy node system makes us to compose the whole shape much easily. It is considered like this. This distance is called LB, and here to here, if it is LA, but we can have a little something clearance or fuzzy area like this. So it comes much more easy to compose. And another system which is difficult to find the feedback system is like this. It is called different bricks. This have like this cone shape, and it is molded like this. And using this foam, thin foam, if we press it, we can make the ellipse-shaped bricks. And when it is stacked like this, we can compose the almost free curve. But the ellipse packing problem is so complicated and difficult to solve. It has found we should solve the simultaneous quartic equations, and that was found not easy one to solve. So I have proposed the approximate how to make it make the approximate solution, and finally we could find like this approximate calculation. It is approximate because you can see around here a little spacing or a little bit overlapped, but almost it is solved. So finally, it could be solved. So we could have the feedback system. But if we could not solve, we cannot have like that feedback, like this feedback system. So considering like this this story, it can come. We can know clearly what we should solve. And here, another idea of using the geometry for structure. This is the cafeteria in Chiba University of Commerce, and I have tried like this roof. It has like these beams, and it has like this diagonal or grid system. And we tried this pattern to have the 1/f fluctuation pattern. It is basically the 1/f fluctuation is for wave, like music or voice or something lights like that. It is said that 1/f fluctuation makes musics or visual patterns like pattern of wood. You can see the lines on the when you cut the wood. That pattern have it is said like this. It has like this character, and it is said 1/f fluctuation makes us comfortable or feeling natural. And so we tried like this pattern for like this roof. And finally, and for like this pattern, I have optimized the columns. Columns are located like this, and I have optimized. And finally, it could be it could have relation with the structure. And I think you should try to find the 1/f fluctuation, or like this spectrum analysis is very much useful for you. I think it is a very simple calculation. At first, you should think the spacings of beams or something values. Will be considered as a progression of spacing, like this. And it is considered as wave. And you should extract these area. It is called fluctuation. And after that, when you have n numbers of values, it is considered as a wave. And finally, you can calculate it with only these three formulae. And you can have like this spectrum. And when we draw the spectrum in a logarithm scale, it is found almost the how to say gradient of -1. And in logarithm scale, and with -1 gradient, it means because the horizontal axis is frequency of wave. This one, f is frequency of wave. So the -1 means 1/f. So it is called 1/f noise. This analysis is very much useful for environmental factors or something design, like color chart or like that. So I think you can try to analyze your design. And all right, in very short. In very brief, I'll tell you how the workshop experiments are. This is done in Stanford University using thin glass. Really, it looks like already like the filter-like structure. And it has only 1.3 millimeters thickness. Leoflex and Dragon Trail is one of the strongest glass. I think it is similar to Gorilla Glass. And students should think about how to control the buckling length. It has almost 2 feet, 2 feet square. But they had to control the buckling length to almost 1.5 feet. So they had to have some ideas how to control or stiffen by this arrangement. And finally, it is found random arrangement makes makes the buckling length shorter. Like this, it is performed also in Tokyo, or like this, and it is found random arrangement is have the possibility. And also this time we could find the fuzzy node system. The holes are previously it is located, so a holes to hole should be adapted or jointed, but we had like this flexible or joint. It is bended or twisted at the site, and we could find finally it has the like this fuzzy node system, and so we could find the hole shape is not so difficult to compose. Looking at here. Like more than 3, 4, or sometimes 5 holes are jointed. It is very difficult to understand in exact exact geometry. Those 4 or 5 points can be located at the same location, but it was possible by fuzzy node. And finally, we could build like this. And other materials, I'm trying like this copper shell, and using aluminum like this floating in the air by helium gas. And carbon fiber reinforced plastics columns. You can see the thin column, this white line, and maybe some of you know it has collapsed. It was crushed by a cat. It was an accident. Accidentally, it has happened. I don't want to think about it. All right. This is the last project. It is called. I'm calling it Nebuta Tectonic. It has like this steel wire and covered by washi paper. Washi paper is the Japanese traditional paper, and it is used like this. We have Nebuta Festival, or in Japan, we have like this float moving for a parade of the festival, and it also have the wire and washi paper structure. Learning from this structure, and we have some other structures using washi paper. It is like this. This is Japanese traditional umbrella, and we use washi paper for umbrella, or like the Nebuta structure, or some kinds of lantern like that. And for umbrella, we need waterproof, so we coat the linseed oil or perilla oil for waterproof. And learning from that, we coated the linseed oil for this structure. And finally, the students studied like this wireworks, and they studied how to, because it is located in exterior, and our campus is very annoying. The big gust will happen in February. And so it had to be resist to 20 meters per second wind. And so we captured the model and tried the drag coefficient analysis and experimentation. This is a simple experimentation. The students put the model onto the bicycle, or they rushed. They rushed again and again. I told him, more faster, more faster. Right. And finally, we could find like this cloud-like freeform is good for drag coefficient. And also like these spheres. Just single sphere is not good for drag coefficient, but some spheres, if it is combined, it comes the drag coefficient comes lower. And with some other experiments for material or anchor plug-in test. Finally, we could practice like this materially nonlinear analysis, and this is for 20 meters per second wind, and it deforms so much, more than 40 centimeters, but it doesn't collapse. So our target was like this. Almost it has 40 feet length, and we could build like this structure, and it has really a translucent structure. And I was thinking like this light and ductile structure, if we could realize for a much more large building, or a real structure, the people will not die even if it collapses by disaster, or like earthquake or like that. It is one of the dream of the structure. So I'm imagining, or I'm dreaming. It's not. I think it's not a fantasy. It will be achieved in some way. And when washi papers are coated with oil, it comes like this translucent material, and it looks like much again the filter-like structure against the lights or like that, or heat or like that. All right, this is all. Or maybe it was so abstract of my handouts, but I think you can know some tips for something useful or for your design or your projects. Thank you.
Very much. That was, I found it absolutely fascinating. I'm biased, I'm a structural engineer. But
sorry, it took a little longer time.
So we have a few minutes left. I've got a whole host of questions that I'd like to ask, but before I do that, I thought I would open it up. Does anybody here have any questions that we can pass the microphone around?
Hi, thank you for the wonderful lecture.
You're welcome.
I'm just thinking, these are very interesting and at a very high level of sophistication in terms of structural engineering that I think most of the students, well, I myself will never be able to reach within the school. So my question is, how good at structure do you think architecture students leaving the school needs to be? How good at structure do architecture students need to be?
I think architect course students it's not so much necessary to understand the exact like mathematics or dynamics or like that. But I think it will be helpful if you could imagine something like it can be not clear. But I think if we could imagine like where's the compression and tension, or like the buckling phenomenon. Who knows the? Is everybody know the buckling phenomenon? Who knows? Who doesn't know? Everybody don't know the buckling phenomenon. Oh, all right.
I'm looking carefully.
I should.
Everyone should know.
I should tell you a little about that. When you press, when you push the something, it shrinks, right? And everything shrinks by compression, right? So this paper is also shrinking. Just a little, but it is shrinking. But finally, I push more, it comes like this. This is buckling. It is considered as like something energy has overflown. And so what is strange is I'm pushing like this in this direction, but it suddenly deforms in this direction. That's the basic buckling phenomenon. And this is so dangerous phenomenon for structure. So we should be so careful about that. So controlling the buckling phenomenon is important. And I told you that the material have the elastic and plastic states. So that is related so much. And so like that buckling, how to control buckling makes the form. We can develop from the idea to control the buckling. From that idea, I could feel the many new shapes are generated. Also in my project. Yeah, so like that, yeah, like that, Junya knows only we should control the buckling length, but he doesn't know the formula. Yeah, like that, if you could know the phenomenon if you could imagine the phenomena, I think you can have some idea to achieve to feedback to your design. Yeah, I think Japanese architects have we learn together, you know. In the same faculty, architect course and engineering course. So Japanese architects have somehow, they're not so good at it, but somehow they know mathematics and dynamics. So we can have communication with them, and we can collaborate. And they are very much interested in generating the shapes related to like that. Geometry or dynamics, I think you know. Yeah, like that, maybe we can, after that, we can collaborate very much, yeah, more and more, I think, yeah.
I have a follow-up on Mark Mulligan I teach here. And Pat and I were very happy about the answer you just gave about the importance of structures classes for architects. So, but my question was about actually a follow-up about buckling. When you showed us the models that had blue and orange and red lines, and
Yeah.
you said the red lines were the dangerous ones.
Yeah, right.
You wrote that program in a way that could control not only for gravity loads, but also for seismic loads or
Yes.
a variety of loads. I wanted to just clarify your criterion for failure for the red is only buckling, or it includes tension, it includes torsion, it includes stress on a joint, or is it only buckling?
It depends on the person how for example, how I input the strength, and basically the joint is not considered. But buckling and some other stresses, compression, axial force, shear force, and bending stress
for a given cross section that doesn't change, or can the cross section or moment of inertia also change in these models? Not automatically.
Yes. If in this project, I didn't have to think the how to say angle or twisting angle of the elements, because we used like this rounded pipe. So we didn't have to think about it. But in like this structure, we should have an idea which direction the section is oriented. Yeah.
Sorry for this one, but is that a plate structure, or is it a truss or a Vierendeel structure?
This one?
Yeah.
This one is a box beam.
Yes, box.
Yeah.
Okay.
Yeah, walls. Yeah.
So I have a non-quantitative question. Some would argue that the engineer's aesthetic guide is informed by our understanding of the flow of forces. You've worked, you've developed your career, you were raised, taught engineering in a climate that is highly susceptible to seismic, to earthquakes. I'm curious how that influences your eye for aesthetic detail. How is the structure's inherent required resistance to lateral forces influence the way you see structural flow in your own aesthetic assessment of buildings and structures?
Do you mean when I look at the structure, the gravity and seismic load will work? And
so people who aren't engineers who are not raised in a highly seismic area view structural flow purely through gravity, right?
Yeah.
But in the culture in which you've been taught structural analysis, its lateral response and its suppleness and all these other far more complex interactions become much more important.
Right.
How has that informed your eye?
I think the gravity, the stress flow generated by gravity is, that's right. Very easy to understand. But for seismic load, for example, using this structure for optimization, when I transform around here, sometimes around here comes red. Yeah, like that. We should know how the horizontal load is transported, and sometimes for earthquake, Japanese structural engineers are taught be very careful about the like roof structure or floor or slab structure should have enough stiffness and strength to transport the stress. sometimes quake-proof wall will not work if the slabs are too soft.
What?
Yeah, like that we imagine how the loads or stress is transporting. Yeah. Yeah, so this software is somehow dangerous for dangerous to give to our architects, but we can know. Maybe they can know by many studies how it is transported.
I'm going to ask one more question, then I'll pass the microphone, because I've got a whole bunch, but I'll limit to one more. Again, the culture in Japan, as I understand it, and you said it yourself, the engineers and the architects, you study together, and there is a very high level of base engineering expertise and knowledge that is assumed the architect will have. How has that influenced the way you relate and you work with architects?
When I'm talking with the architects, I'm feeling, I'm looking, the architects cannot tell so precisely about which structure they are imagining, or which dynamics they want to control, or geometry. So I'm feeling I'm always at the meeting or discussion with architects. I'm looking for what they are imagining. It is not clear, but my mission is to find or to make it clear how the structure, which structure is are they imagining? Yeah. So I propose many kinds of structures, or I draw, or I make many sketches at in the meeting, and I make like this calculations so much, and I tell them how the members or elements, which dimensions the elements can have, and so finally some idea will be generated, and we can say, oh, let's go with this. Yeah. Yeah.
Okay. So the good news of that is it doesn't sound that different from the way we have practice here in the U.S. But I think the importance is that there needs to be a base level of understanding of comprehension on both sides of the table, so you can have that conversation. I think we have time for one more question.
Yes, I like your concept of dangerous software. It is true. Software can be dangerous. My question is, have you worked with 3D printing? It seems that your fuzzy nodes would be a perfect application for that.
Not yet. I have performed in like this actual project, but with like building temporary structures for something events. My lab have. Students in my lab has tried just once, but using like this piece of 3D printed joint, using like the joints, and they built the Latin structure. You know, Latin kind of plants. Using the rattan. Yeah, rattan. Yeah, structure. So I think it has the possibility to use 3D printing, 3D printed joints. I think there are already metal or using metal for the 3D printer. Yeah, so it has a possibility to use it, and This is the I think this is a good sample, or we can when we could develop like that flexible or joint. It has it is very much useful for like this fuzzy node system. Yeah.
Okay. Well, thank you all. Thank you very much for a fantastic presentation.